Hello again, and welcome back to my homemade 8-bit CPU. As I promised in the last video, today we're going to have a closer look at the clock module, which is this module up here in the corner. Ben Eater's video series goes into detail into how to build this clock module over several episodes, and I've posted links to his videos in the description of mine. And today we're just going to have a look at the one or two additions I made to his clock module. And also we're going to have a little look at the power distribution, which I've organized a little bit differently from him. So let me just get the camera set up so we can have a closer look at the clock module. So here we see the power and clock module from close by. And first of all, I'm using exactly the same Apple 2 amp charger that Ben was using, which you can see here if I tilt the camera around. And I'm using the 5 volts from the USB off there, but I'm inserting it into my board using essentially a plug, which I can just plug a standard USB cable in rather than having to cut into a cable and getting the wires out. So if I turn the power off here, then I can show you. So basically I just have a 4-pin plug here, and of course I'm not interested in transmission and receiving. I'm just interested in the power and ground. And so you can get these plugs, that's what they look like, which allow you to just plug any USB cable into a breadboard. So that's what I've done, so let me put that back. And as you can see, as I just did, one of the things that I wanted was a power switch. So I have a power switch here, which allows me to have the board not be powered even though the USB cable is plugged in, because I just want a switch to turn it on and off. You might think, well, that's easy enough. All I have to do is take my 5 volts here and just put a switch here. So I can disconnect it or connect it to my circuit and just leave my ground connected at all times. And then I'll have 5 volts and ground powered up here or not, depending on what the switch says. And then I can hook up an LED here with a current limiting resistor to show that my power is on. And here's a capacitor, which is, Ben Eater talks about this capacitor. It's used to counteract any impedance in the lead USB cable coming from the power source. So okay, that seems simple enough. But then I had a look at the datasheet for the switch, which I'm actually using. As you can see here, it's actually rated for a maximum of 0.4 watts. And so if we're powering our circuit at 5 volts, which we are, then that basically means a maximum current of 80 milliamps. And so in Ben Eater's videos, he talks about his power at one occasion, and basically his computer is drawing 1 amp. So that's way more than what that switch can handle. So we can't use that switch here because we're going to have the full amp being drawn through directly from the 5 volt power source into the entirety of our computer. So with the switch that I have here, this is going to cause problems. And so I made a small change to that, and we're going to use our infamous transistors. Basically, the transistors are electrical switches. And so what we have here is we have that same switch, and this time it's connected in series to the LED and the resistor to show me that I have power. But it's connected to the, it's allowing a base current from the emitter to the base. This is a PNP bipolar transistor. It's not a usual NPN because, of course, I'm connected to 5 volts, not to ground. And so we need to reverse things because I have a current which is in the conventional sense running from the emitter to the base rather than from the base to the emitter, as you would in an NPN bipolar transistor. But so, okay, you can find PNP transistors easily enough. And so I went ahead and found one of those. And so what we have here is basically we just have the few tens of milliamps, 10 or 15 milliamps, which is running through the LED, which I can turn on or off using this switch. And that's basically going to control whether my 5 volts here is connected to the rest of the circuit. And of course, through this transistor, I can have a collector current which is determined by the transistor, not by this power switch. So this power switch is going to have very little current, just enough to light up the LED, but it is going to allow me to control whether let's say the full current of my computer is running through, is connected to my power supply or not. And so you need to find a PNP transistor. They're basically power transistors. So the one I have is rated for 1.5 amps, which I thought, well, you know, let's just see how far we get with my computer. Now, as it turns out, I did some measurements. In fact, because of some of the changes I made, my computer draws around about 300 milliamps, so substantially less than Ben's, for reasons that, you know, I didn't plan on initially, but of course I'm happy about that. But anyway, even 300 milliamps would have been too much to, you know, push through this switch. So I think this is a good solution. And it allows me to showcase the, let's say, the textbook use case of a transistor. And so here is that PNP transistor, this thing in the corner here. And so right on the left-hand pin is the base. And so as you can see, that's connected to an LED and then a resistor, which is running to ground. And the collector is the middle pin on this transistor. And so the middle pin is basically what I've connected to the 5 volts all around my circuit. And the emitter is connected to the actual 5 volts coming out of the USB power supply. So even though it looks like nothing's on at the moment, there is actually 5 volts between the ground and the emitter of this transistor. But because this switch is off, there's no current running through the base. And so the collector, which is in the middle here, is not connected to my circuit. And so my computer is not running right now. But so if I turn on the switch, okay, then we have a base current, which is just enough here to light up this resistor. And so the rest of my circuit is powered. And now, of course, I just powered it on, so the program which is in there at the moment is nonsense. And since it's complete random, well, sooner or later it's gonna run into a halt instruction. And so the computer stops, and we're gonna talk about the clock right now to see how that happens. But so basically every time I reset it, it's gonna run a few cycles until it gets to a halt instruction. And then it's gonna halt until we actually encode a useful program in there, which hopefully doesn't have any bugs and doesn't halt. So let me just do that quickly, put a program in there to make sure that we don't run into halt. And so now the computer is running basically a program in an infinite loop, so it shouldn't halt ever. And as you can see, it's running on the automatic clock signal right now. And just as in Ben Eater's design, we use a 555 timer here in astable mode to produce a periodic clock cycle. We could even have a look directly at its output. So remember, the output on a 555 timer is pin 3. So let me just connect pin 3 of that timer to ground. And you should see the oscillating signal, which right now is the same as is going into our clock. But of course, you also have this switch here, so we can switch from automatic to manual clock mode. And so when I switch that over, you'll see there is no longer a clock signal, but of course that 555 timer is still oscillating, and so we're just not connecting that to our clock signal right now, because we've moved this 555 timer, which is basically what Ben Eater calls the bistable mode, is configured to look for a manual clock pulse, which is this one right here. So at the moment, this is what happens. So I have a manual clock, and we're using, to get that, we're using a 555 in monostable mode to basically to debounce our circuit. So no matter how long I press that, it's gonna be on for about half a second. And so we can also connect an LED to the pin 3 on this 555 timer to see the monostable pulse. And so when I move my clock back to automated mode, now the oscillating signal is going to our clock, and so whatever I do on the manual pulse here is totally irrelevant. So that is still working, and it's just not connected to our clock signal right now. Now, one change I did make compared to Ben Eater's design is in the monostable mode. So let me just switch that over to monostable mode, so manual pulse mode. I believe Ben Eater uses a 1 mega ohm and the 0.1 microfarad capacitor, which gives him a time constant of 100 milliseconds. That's 1/10 of a second. And so Ben Eater's pulses, when he pulses this, are debounced and are guaranteed to be 0.1 seconds long. Now, for whatever reason, when I was debugging this computer using instructions and going through step by step, I found that I was still getting double basically double clock ticks from pressing it once. And if you think about it, the reason is that even though when you press this, the rising edge of the clock is debounced. So as soon as I press it and there's a single contact, the latch will get set and it won't reset until the time constant expires. But if for whatever reason I keep this switch open longer than that time constant, when I release it, I'm going to reset, and so the falling edge of the clock isn't debounced. And so what could happen is that when I release, there might be another contact, which is going to cause another rising edge and another time constant to expire. And so when I had Benito's values, which gave me a time constant of 0.1 seconds, I don't know, for whatever reason, I guess I touch more slowly than he does, I was getting debounces. So what I did was I just changed the parameters a little bit. So I now have here a 270 kilo ohm resistor and a 1 microfarad capacitor. And that basically gives me a time constant of 270 milliseconds. And so my debounces are almost 3 times longer than his. And so for me, that works well, just, I guess, because I have slow fingers. And so here I've drawn a little schematic of the clock module. So here we have the A-stable 555 timer. So it's connected to 5 volts and to ground. The reset pin is tied high, so we're not using that at all. And so we tie pin 2 and pin 6 together, and then we have this huge variable, well, huge, sometimes huge variable resistor connecting it to pin 7. And then a fixed 1 kilo ohm resistor connecting that to 5 volts, and we have the capacitor here. And so this capacitor and these resistors together are going to determine the oscillating frequency. This is this infamous capacitor across pin 5, once again just to clean up any glitches in the power supply. And on pin 3 we have the output here of the A-stable timer. Then we have the monostable clock, which is over here, which allows us to pulse manually. So we've connected that to a trigger, and once again we have a capacitors times 6 and 7 are directly shorted to each other, and we have this capacitor and this resistor, which together determine the time constant of the manual pulse. And so I tweaked these values a little bit. In my configuration, this is 270 kilo ohms and this is 1 microfarads. So further details about these circuits, I really refer you to Benito's videos, because they're really excellent on the subject. Finally, I have my switching signal here. So this is the bistable mode, where we're basically just using the latch. So we're using the reset and the trigger pins, but apart from this capacitor, which is just there to clean up glitches, we're not managing any time constants in here. And so the output from that one is going to be a 1 or a 0, depending on which clock I'm interested in. And so we basically need a bit of logic, which is what we have over here. And here I made some changes compared to what Ben did. So in his video, Ben goes through explaining how to build a selector to build the final clock signal based on a selection using some AND and OR gates. And he explains very rightfully that you can do the same with NAND gates, and it saves you a chip. So I did exactly that. So my design uses NAND gates. We have our selector, which is coming out of this timer here. And so in one case, this is going to be 1, and in the other case, this is going to be 0. So I'm using some inverters and some NAND gates. So that's 2 chips instead of 3. So in the case that this is set to 1, then I am going to take in the automatic signal. And because this is a NAND gate rather than an AND gate, I'm going to get the inverted clock signal here of the automatic mode, in case we've selected automatic mode. And if we haven't selected automatic mode, then I'm just going to get a permanent 1, because this is an AND gate. And here we have the opposite. So if this is set to 0, this selector, then that means I want the manual clock. And so I'll get the manual clock signal here. And so if this is set to 0, then this is going to be a 1. And so then this NAND gate is going to be active, and it's going to invert the manual signal. And so again, here I'm going to get the inverse of the clock signal if I've selected the manual pulse. And if I haven't, I'm just going to get a permanent 1. And so here we have another NAND gate, which takes, on one side it's going to have a 1, and on the other side it's going to have the inverted clock signal. Or in the opposite case, it's going to have a 1 here, and it's going to have the inverted automatic clock signal here. So in both cases, it's going to have a 1, which is NANDing together with some clock signal. And so that's actually pretty good, because that means that we're going to get the desired clock signal, and we're going to invert what we input in here. But since this is the inverted clock signal anyway, we're actually going to get our desired clock signal right here. So I could simply hook up that and say that's the clock signal, and we'd be done. Of course, just as Ben-Eater does, I also want to be able to halt the clock from the control logic. So I provide an extra input line here, which is the halt line. And I've set that to active low, because that simply means I can use another AND gate here rather than NOR gate. And since I have, or NAND gate, since I have NAND gates, that's good, because I have 4 NAND gates on one 7400 chip, so that's good. So I've simply taken the convention that I'm going to work with the active low halt signal. So when this is 1, that means I'm not halting, then I'm simply going to invert my clock signal, and because I want the real clock signal, I have to invert it one final time to get it here. But if this ever goes to 0, well, then this NAND gate is going to output a permanent 1, because it's going to AND 0 with whatever here, that's going to be 0, and reverse, that's going to be a 1, and I'm going to reverse that, and so I'm going to get 0. So when the clock's halted, I'm not going to get any signal. I'm not going to get a manual pulse or an automatic pulse. And so that's basically how I've used the optimization that Ben-Eater proposes in this little circuit here. Now, one rather important difference between my computer and Ben-Eater's computer is in the technology of logic gates that I'm using. So Ben-Eater basically uses mostly chips from the 74LS series, which is a logic gate series. And if you Google on Texas Instruments logic guide, you can find this useful information that Texas Instruments has written, describing the various generations and technologies which they use in their digital chips. And so if you look a bit further in this guide, you'll find a description of the technology that Ben is using, which is basically here the LS series, or the Schottky logic series. And so they use Schottky PNP or NPN bipolar transistors. And so, well, bipolar transistors are current-based, so they're going to be drawing a small but still non-zero amount of current whenever they're on. And that's how they work. And while I was trying to order parts to start building my computer, it transpired that a lot of the LS series chips were often simply unavailable or on back order, so they couldn't be shipped immediately. And it turns out that there are actually more modern families of chips which are much more readily available, and especially here in Europe. I kept finding that chips from this HC and HCT series, which is this here, based on CMOS transistors, are much more readily available and usually in stock and can be shipped very quickly. And so I had a look in this guide to find out the principal differences. So basically, you have HC and HCT, which use the same technology. They use CMOS. The big difference is explained in the beginning of this guide. So if you look here, the big difference is, some circuits are still going to have the odd TTL chip based on bipolar logic in there somewhere. And of course, they used different sorts of logic levels. And for example, on the bipolar transistors, you can actually hook up LEDs directly to the output pins. And when they're set high, there's actually a pull-up resistor in there, which is also going to limit current through the LED. And of course, when current is flowing through that resistor, well, the voltage is going to drop. And so it can actually drop all the way to 2.4 volts. So anything above 2.4 volts on one of these LS chips is still considered to be a high signal. And if you go to a pure CMOS chip, well, that's not the case. So if you would have some signal which would drop to 2.4 volts, it would be totally indeterminate here what that might be. And so the chip manufacturers recognized this problem, and that's why they came up with what's called the HCT variant of CMOS. And so they have some, internal engineering in them, which makes them basically logic level or voltage level compatible with TTL logic. And so that's the series that I've gone with. That's this HCT series. And so it gives you the advantages of CMOS, which basically means they don't draw any current unless they're switching. But they do have logic levels, which means you can actually mix them and integrate them together with the odd LS chip. And in fact, in my circuit, there are a few instances where the 74LS variant was available and I couldn't find an HCT, so then I took that. And because I'm using HCT rather than HC, I'm not having any problems. So that's a big difference, and I suspect it's one of the reasons why I'm drawing less current than Ben Eater, because I'm using, let's say, a more modern technology. But of course the logical functions of all these chips are identical, so wherever Ben is using, say, a NAND gate, which would be a 74LS00, I'm simply using a 74HCT00, which is logically exactly the same, even has, you know, these same voltage levels, but it's using CMOS technology rather than bipolar transistors. So that's just about it for today. We had a look at the power and the clock module up here. And so once again, many thanks to Ben Eater for his inspiration. I was able to use his design more or less unchanged. Made a few tweaks here. The most important one is that I increased my manual clock pulse. Have a look at his videos to understand the details of how these different 555 configurations work. Anyway, so next video, what I plan to do is have a look at the registers. So as I explained in the introduction, I have 4 general purpose registers: an A register, a B register, a C register, and a D register. And they're not doing very much right now because the program that's running is exceedingly simple. It's a really tight loop. But so we'll have a look at how those registers are built. So see you in the next episode.